Okay, great. Thanks a lot, Jesse. Okay, so today I'm going to talk to you about X-ray beamline modeling with SRW and Shadow. Um, and this is my outline for today. So I'm going to give a short talk, about 15 minutes or so here, and present some of the background about the codes that we're going to be using and how they work in Sirepo and some of the extra tools we've built. And then I'm going to do a demonstration of how to use them. So I'm going to start with X-ray optics, a little bit about X-ray optics, talk about SRW and Shadow. Then I'll talk about SRW and Shadow in Sirepo and some of the extra tools we have, and then do the demo of building a Kirkpatrick-Baez beamline in SRW and Shadow. Okay, so X-rays are our topic here today, and you know that when you go to the dentist, you get X-rays, and they come out of something called an X-ray tube, which I have a little picture there. There's a lot of other sources of X-rays in the world. Inverse Compton scattering is one way that we can create X-rays. There's also astrophysical sources of X-rays. Excuse me. But today we're going to be talking about X-rays in synchrotron light sources. So those either come from the dipole magnet or an undulator magnet. And if the electron beam is kind of random, then you end up with incoherent synchrotron radiation. And then we also have cases where you can set up a microbunched electron beam, and that will give you more coherent synchrotron radiation in a free electron laser or X-ray free electron laser. So there are 4 different synchrotron light source facilities in the U.S. There's the ALS, the NSLS2, the SSRL, and the APS. And there's also there's a large number of facilities around the rest of the world. And I show a couple further here: the ESRF in France, the MAX4 in Sweden, the Taiwan photon source in Taiwan. Okay, so we're going to be talking about these facilities and some of the modeling involved. So just as an overview, if you have a electron gun, this is basically the setup of a synchrotron light source for anyone who doesn't know. You have an electron gun producing the electrons, then it gets accelerated in the linear accelerator, then further accelerated in a booster, and then accelerated into the storage ring. And then the electrons stay in the storage ring, and then they pass through magnetic fields, either in the bending magnets or the undulators, to produce the radiation that passes down the beamline and then goes to the sample. And then you do some experiment using the interaction of the X-ray and the sample. So there's a lot of different kinds of modeling that happens in this whole process. And many of the codes are actually available in Sirepo, and there have been some other seminars webinars people have given about them. The beam dynamics, we have the codes Elegant and MADX in Sirepo for the magnet design and modeling. There's the Radia code, and now here we're going to be talking about the X-ray optics with SRW and Shadow. And then we also have machine learning applications called Activate, and a control systems application called Controls. Okay, so the elements, an X-ray beamline is composed of many different elements. We have focusing elements and energy dispersion elements. The focusing elements are the mirrors, the compound refractive lenses, zone plates, and there's also just a simple lens. So these are the elements we're going to be working with, and then an energy dispersive element, that's for making a monochromator, for example. We have crystals and gratings, and then there's physical apertures. You can have apertures and obstacles to and the apertures and obstacles reduce the beam size, and they increase the coherence of the radiation. So there's kind of two different goals one might have in doing beamline modeling. The first is when you're designing a new beamline, you want to do some design work, and so right now there's a lot of projects upgrading storage rings to ultra low emittance near the diffraction limit, and so this involves a lot of upgrades of beamlines as well. And in addition, just at any facility, there's always new beamlines being developed or upgrades of existing ones. Further, the second concept is that when you're actually running a facility, you'd like to be able to model the beamline you're actually working with. You might be changing parameters, the energy, the beam size, moving from a steady state to a timing experiment, and this requires some tuning of the beamline, and it can be time consuming. And so although this isn't done as much as perhaps it could be, having a model of your beamline while it's running and using existing diagnostics to tune that model can be really helpful as far as more rapid transformations of tuning of your beamline. So two of the main codes that are used in this domain are SRW and Shadow. SRW is a little bit has more capabilities. It includes partial coherence. It includes diffraction effects, but it's also a challenging code to use, and you have to be able to set the propagation parameters correctly. You have to understand how to do a partially coherent calculation. You have to make sure your elements are set up correctly. Then there's also several interfaces to it. There's an Igor Pro interface, a Python interface, and two different. There's a kind of low-level Python interface and a virtual beamline interface to SRW. And you just have to be careful when using SRW to make sure that you actually get results that make sense. And so one of the things we've been trying to do is build in extra tools to be able to cross-check your results. So maybe you then see, okay, that's not what I want, and you need to change some parameters to make sure that the Fourier optics is getting done correctly. So yeah, overall, SRW, which is developed by Oleg Chubar at Brookhaven. It's a wavefront propagation tool, and it can model bending magnets, undulators, and wigglers, and as well as arbitrary magnetic fields. You can do partially coherent propagation in several ways, either sampling the electron beam distribution or doing a coherent mode decomposition. Shadow is geometric ray tracing. It was originally developed by Franco Serena in the 1960s, and it's maintained by Manuel Sanchez del Rio at ESRF and Luca Rabuffi at APS. It's sometimes you can think of it as a first pass calculation, but in certain cases it's going to be good enough and give you some good enough accurate results. It creates a set of rays that that exist in phase space, so it kind of gives you a different view. It's easier to look at the phase space of the optics, and then those rays get propagated through the beamline. Although without some extra additions, it's not, you're not going to be able to include the diffraction effects. So yeah, just as a summary, it's SRW has a bit more accurate physics in it, but it's also challenging to use. And Shadow is faster, less error prone. You can more easily get the linear optics, and it's easier to visualize the optical phase space. So one of the tools we've added is, well, here's a kind of summary of some of the tools we've added. So we have analytical brightness calculations, and there's a webinar about that, and I'll talk about that in a moment. We have the coherent mode decomposition. We have 2D and 3D beamline layout visualization. In Shadow, we've added a linear optics with Gaussian aperture capabilities, and then in SRW, we've added machine learning data generation. And we're developing something called linear canonical transform propagation using transport matrices that are calculated in Shadow. So this is the brightness calculations. This is kind of an analytic expression that's nice to see that you've set things up correctly. So we actually have a paper where we cross-checked these formulas with the SRW calculations. So with a bit of digging and using these tools, then you can cross-check your results and make sure you're getting reasonable results. And this also can include the effects of energy spread and being off resonance in an undulator. And so you can compute the flux, the brilliance, the angular flux, and then the RMS beam sizes and divergences, either varying the undulator gap, or that's called K-tuning, or spectral detuning is moving off resonance. Okay, now this is a recent addition that we've been working on. This is in Shadow. So what we've been doing is using Shadow to calculate a transfer matrix. My background is in beam dynamics, in particles, and so there we very often compute transfer matrices down a linear section through a quadrupole or something, and you can do the same thing in optics using the ray tracing to use rays to calculate a transfer matrix, and then that can be used to propagate a second moment matrix. And this is actually more general than it at first might appear. You can actually, this is called a Gaussian shell model, or a Gaussian Wigner function. And so it includes partial coherence. You can calculate a coherence length. There's a fair amount you can do with this. And we've also added the effect of Gaussian aperture. So a hard edge aperture can be approximated by a Gaussian aperture, and we've been working to find the ideal size of that Gaussian aperture that best fits it. So within this model, then you can propagate the Gaussian all the way down the beamline that includes the apertures as well. So this is a nice kind of I think of it as linear optics basic check that you can do to see that your optics are set up correctly. And there's some papers and some formulas for how the beams changes when it passes through the aperture. Coherent mode decomposition is another important algorithm. There's a recent paper by Lee and Chubar, and Oleg implemented these formulae, and what you can do is do a decomposition of the initial mutual intensity function into these coherent modes, and then you can propagate those down the beamline. So instead of having to do, sometimes you need to do 10,000 or 100,000 macroparticle propagations. Now you can just, you may only need 10 or 100 coherent modes when when you do the mode decomposition. And there's also, I recommend the paper by the thesis by Mark Glass and other papers by him and Manuel Sanchez del Rio on this topic. So that's implemented now in and available in the virtual Beamline Python interface and also in the Sirepo interface to SRW. Finally, I'll mention that once you've set up your simulation, either in SRW or Shadow, what you can do is download that to, you can download a Python source of that. And so you get a Python file, and you can go to the Radiusoft Jupyter interface, and you can take that Python and paste it into a notebook, and it should just work because we have SRW and Shadow already installed in our Jupyter interface. So finally, what I'm going to do next is walk you through the creation of a KB beamline. This was originally, this is sort of one of the simplest but used beamline optical layouts, and this is designed by Paul Kirkpatrick and Albert Baez in 1948. Albert Baez is the uncle of John Baez, the mathematician, and Joan Baez, the singer, folk singer. And so this is basically what it is they're elliptical mirrors, and elliptical mirrors turn out to be kind of perfectly linear. They don't have aberrations to them, and so you have both a horizontally focusing and a vertically focusing KB mirror, and those KB elliptical mirror, and those together will give you a focus to take your source to the sample. And I've included an aperture here at one point. I'm going to include an aperture as well, which is common to create to have some control over the initial beam size, and also to impact the coherence properties. Okay, so let's try this out ourselves now. So I'm going to switch over to the web browser now. Let's see. So I want to. Okay, so here's the web browser, and just to, let's go to, so here we are at Sirepo.com, and I suggest, if for all of you, hopefully you have Sirepo accounts, and so you just go to Sirepo.com, and now here's the supported codes. So we're going to go to SRW here. So yeah, I suggest trying to follow along with this. So then you'll find all of your folders of the different simulations you've created. So here is, let's see, so the webinar, I'm going to create a new folder called webinar. And now I go into that folder, and now I'm going to create a new simulation. This is a new SRW simulation, and I'm going to call this KB Gaussian beamline. And the source type here, so I'm going to, these are the different options you have for the source type. So I'm going to start with the coherent Gaussian beam. So we save changes. And now here we are. So now we're in Sirepo. If you click on the pencil here next to coherent Gaussian beam, you can see the parameters. So this is 9K. So you need to tell it what the energy is. So at the moment, these are the default values. So this is 9 keV. The polarization, which direction the electric field is pointing, is linear horizontal. Now the beam sizes. So the default value here is 9.8 miles for both the horizontal and vertical. And if you can see that the divergence is set for you, and that's because we're coherent, and so we're Gaussian, and so we satisfy the equation that the sigma x times sigma theta is lambda over 4 pi's. So so that's gonna, so by setting the size, that determines the divergence. Okay, so we save that just to have a look at those parameters. And now you can see it says simulating, and this is an intensity of 20 meters. And so now it shows you what this Gaussian is going to look like at 20 meters. Now you can plot various quantities. So right here we're plotting the intensity. You may also be interested in looking at the real or imaginary parts of the electric field, and that will do that calculation. And so you can see here it is that we're not at a waist, so we have something a little bit more complicated for just a Gaussian beam. I'm going to go back to the intensity, and I'm also going to set this color scheme to Viridis here. So this is the source page. We're going to come back a little later to this and show how to create an undulator source. But for now, let's go over to the Beamline tab. So click on the Beamline tab, and now you see all of these different Beamline elements. So to create the KB beamline, we want to select the elliptical cylinder. So drag and drop the elliptical cylinder down into the beamline definition area here, and I'm going to call the first one KBH. So that's the name, and then I want to put this at I'm going to put this at 28.5 meters. So if you, just as a brief overview, we see we have these different tabs available. The name and position, the geometry will set the focusing optics of it, orientation will tell you whether it's horizontal or vertical and allow you to do rotations or misalignments, and then height profile would allow you to include errors in your mirror. So let's go now over to the orientation tab, and we can see that first there's a very important parameter, the grazing angle. So just let's say we want to increase that a little bit. So we have a larger grazing angle. Let's change it to 36 milliradians. And you can see we're set at horizontal. So that's fine. Now I want to go back to the geometry tab, and this is important to get the focusing right. So it says it's 20 meters from the source, which is that one's less critical, but the Q value we want to make sure is set to be the distance to the focus, and so that we're going to set to 9 meters here. So, and then the tangential size and sagittal size, that gives you the apertures, the physical size of the mirror. So we close that. So that's the first mirror. Now we're going to make a second mirror. So let's bring down a second one. And you can see that by default it has moved it 1 meter away, so we're at 29.5. Now let's do the same thing. Let's go to the orientation. We're going to increase the grazing angle to 36 milliradians, but now we want it to be a vertically focusing. So under auto compute vectors, we're going to select vertical here, and now you can see that the normal vector is largely pointing in the vertical direction. And now we go back to the geometry tab, and this one, so now we want to set this to 8 meters. So the distance from the mirror to the second focus is 8 because we want to have the focus be at the same place for the two, for horizontal and vertical. So we close that. Now we want to add a watch point so we can see what it does. So select a watch point and drag that in here, and I'm going to put that at the position of the focus that we've been setting up here. So I'm going to put that at 37.5, which was 9 meters from the first and 8 meters from the second. So we close that. Oop, I made a mistake. Let's change that. We don't want the element name to be 7.5. Let's call this sample, and then the position is 37.5. Okay, and I meant to name this one KBV, so let's go back and name this. So you're always able to go back and make whatever changes you need. So this is our simple KB beamline, and let's now see what it does. So first thing to notice is you can go to this 3D beamline tab here, and this should kind of give you a bit of the geometry. This should show you what you've created here. So now you have this diagram here that shows the KBH and KBV in the sample, and you can see there's a small angle associated with it coming from the grazing angle. So that's the beamline that we've created. Now we go back to coherent results, and now we click on Start New Simulation, and so this should now take the Gaussian beam that we created in the source and pass it through this this beamline. And so here we are. So here's the initial intensity at the first optical element, which is the horizontal KB mirror, and here we are at the at the sample, and you can see it's substantially smaller, so it has focused it, so it's down to much smaller here, so a couple microns, whereas it was more in the 10s and 20s of microns for the RMS or previously. So this all looks good, but you can kind of notice that it doesn't look so great as far as the resolution. So that's not so good. So now we see where we need to go in SRW to make some changes to get this to work. So let's click on the initial wavefront here, and now we have some parameters we can adjust. So what we want to do here is adjust the sampling factor. We're going to change that to 4 here. Save changes, and let's try that again. So that should now, that's one of the simplest things you can do. It just increases the resolution of the incoming radiation, and that's going to then get passed down the beamline. So you can see we have succeeded in increasing the resolution here. But you'll notice that we're kind of wasting some space now. Now the range is a bit too large, and so it might be better to reduce that. So now I'm going to show you, if you go up into, click on this propagation tab here, you can see that each of the elements now in the beamline has a number of parameters that can be adjusted, and these are the propagation parameters that are very important for any kind of Fourier optics code, and we bringing them out here in SRW in Sirepo. And so you can see that there's propagators. You can specify a different kind of propagator for each one of the elements. Resizing on the Fourier side. The main parameters I like to adjust here are the range and modification parameters. And the easiest thing to do is to just go to the end here. And so we're going to reduce the range factor. So we're going to make 0.2 for the horizontal and vertical range factors. And just to let you know, if another way to increase the resolution, you can also increase the resolution. So let's increase by a factor of 2 the resolution, the horizontal and vertical resolution factors. Okay, so that should be just making some adjustments at the very end there. So we close, we save changes, and we start a new simulation. Pretty fast. It should take a little bit longer from the initial result, since we've increased the number of points in from the sampling factor. But now you can see that it's better centered, and we're not wasting as much space here by taking a very large range. So that takes some experience and some playing around. So you have some. We give you these parameters, and you can kind of do some experimentation on them to see how they impact the results. So yeah, I think we have a pretty good result here for the passing of a Gaussian beam, a coherent Gaussian beam through a KB aperture, KB mirror. The next thing I want to show you is that we can now bring this simulation into Shadow. So if you go under this cogwheel here, and now you have these options, open as a new Shadow simulation. So I'm going to select that, create a Shadow simulation with an equivalent beamline. Yes, I'd like to create. And now it has created the Shadow simulation for you. So I'm going to click on that. And now if you look at the URL, you'll see that now we're at sirepo.com/shadow. So we're now in the Shadow code, but all of the parameters have been translated over. So we now have our KBH and KBV mirrors and a sample. One aspect of Shadow is sometimes you need to do a coordinate transformation as you move along the beamline, and that's what's happening here between the horizontal and vertical mirrors. So let's briefly look over at the source page. The source has been created as a geometric source, as a Gaussian, and with the sigmas of 9.8 microns, and then it has 100,000 rays, a seed value for the randomness. So this specifies all of the rays, and now we can go back to the beamline, and you can see this is Shadow. So this is at the initial, right before the first KB mirror. You can see what it looks like, and at the sample as well. I'm going to briefly show you that you can, so something interesting, you may want to look at what the phase space looks like. So let's do XX prime, for example. And so I'll do that change here and show you. This is kind of, so you can see you have a tilted beam, and if you're familiar with phase space dynamics in charged particle beams, you know this is what you get when you have an initial Gaussian that drifts, that moves along in empty space, and it just drifts. So Shadow really gives you a nice way of visualizing visualizing the beams. So I'm going to go back to the I'm going to go back to Z here. Okay, now hidden down below is this other report that I wanted to point out. So this is this beam statistics report that that I mentioned in the introduction. So here you can the sizes as they move along and they hit the lens, the mirrors, and then they get focused. So what I want to do now is add an aperture and show you that this can take apertures as well. I also want to put an additional watch point a bit further along. So let's put this at 45 so that you can see further how the optics is progressing. So that's one change. The other change is I wanted to add an aperture. So let's add an aperture at 14 meters. And I wanted to make it a bit smaller because we want to really cut into the beam size just to show that. So I'm going to cut it down to 10 microns. So we're in millimeters, so 0.01 will really cut it down. Let's do that in both the let's do that in the horizontal, and let's say we're at oh, we'll do the same thing for both the horizontal and vertical. So now I've added that aperture at that needs to be at 14 meters. Okay, so we save that. So that will then rerun the calculation, and we've also added, I don't want to call that 45, I want to call this past sample. Save changes. Okay. So here we are. So you can see that we've really cut into the aperture. Past sample, what happened there? I didn't want 38.5, I wanted 45 here. Okay. Yeah, so here you can see, now you can see the impact of the aperture, and it goes all the way up. And so you could, by setting the initial sizes, Shadow doesn't require you to actually be fully coherent. So you could set the Gaussian beam sizes to be whatever you want them to be, and then it can represent a partially coherent beam, and then you will get the right results as you pass through the aperture for how a partially coherent beam would be. One interesting thing to note is that the waist doesn't occur at quite the same position between horizontal and vertical, and that's because the sizes are a little bit different, and the focusing of Gaussian beams has a factor of the Rayleigh length in there. So there's a little bit of a difference in where the waist occurs due to the Rayleigh length. And so there's really a lot you can learn by studying pictures like this. You can see that you've set things up correctly and change the sizes, and just see whether your beamline is doing what you expect it to do. So I think of this as one of the nice tools in if you're not sure that maybe you've put a lot of complicated elements in there and you're not sure the propagation is happening correctly in SRW, you can go here and check in this shadow beam statistics report and see that, okay, at least I've got my linear optics right, and I would expect a beam size around this big, and then you can go back into SRW and see that you're getting something close to what you expect, and then maybe you need to make some changes in the propagation parameters. Okay, so now I want to go back to the SRW here, and I'm going to show you now how to include the undulator radiation. So I'm going to go back to the simulations, and I'm my KB Gaussian beamline. So open as a new copy, and now I'm going to call this KB undulator radiation beamline. Create copy. And now if you click on this, the name here, you have an option to make a change here under source type. So I'm going to select electron beam with idealized undulator, save changes. Sometimes at that point you have to refresh. Okay, now I've created a undulator source. So electron beam here can look at the parameters. These are the default parameters. This is parameters for the NSLS2 low beta results, and you have 3 GeV, a current of 0.5 milliamps, an energy spread of 8.9 times 10 to the minus 4, and then you can specify either with twist parameters or directly with moments. You can say how big the electron beam is going to be. So that's the electron beam, and now it should go ahead, and then the undulator is the other parameters one needs to set to determine the radiation. So just quickly, you can see this is set to a period of 20 millimeters, a length of 3 meters. It's calculated the K value for you. If you click on the pencil here, you can go in and see it's a magnetic field of 0.887 Tesla in the vertical, and so this allows you to, you could make it an elliptical undulator. You have some different choices for how to set up your undulator here. And now you can see we've got a large number of results. We've got the spectrum computed. You can see that there's always going to be missing. In the ideal case, you don't get even intensity on the even harmonic. So 1, 3, 5, 7. Here's the electron trajectory passing through this undulator. Here's a non-idealized. This is an aperture with a little bit of size, a finite aperture, so you can see that you do get a little bit of flux through on the even harmonics. The total power density is kind of an integration over all of the energies, and then the intensity here is at a particular energy. Here it's at 9 keV, which if you go back up, you can see was at the 5th. That's going to be the 5th harmonic there. Now here's the coherent mode decomposition. I don't have time to demonstrate that right now. Here's the brightness report that allows you to do either the K-tuning or the spectral detuning. You can select from all of these different options: the flux, the angular flux, the brilliance, or the sizes and divergences. And so those will use those analytic expressions, and that includes the impact of energy spread, and also allows you to go off resonance. So a lot of nice calculations could be checked in that brightness tab. Now finally, we're going to go back over to the Beamline tab, and So this is already set up as a KB beamline, so we're going to start the new simulation. And now it's going to take the undulator radiation and pass that through the beamline. So here we are. We've got our, so you can see here's the initial radiation, and you can see that the size, it's not quite fitting within the window. So we're going to have to go in and change that. I'm going to go to the initial wavefront, and instead of 0.4, I'm going to change that to 1 and 1. These are the just increasing that window there. And then we'll see that this is the undulator radiation, because it's kind of this sync sine x over x shape distribution. So we have a little bit larger range, so it takes a little bit longer. So I think let's check. I'm going to also check over here. Go back to the SRW. I have a backup there just to open. Here's the undulator. This one's substantially larger. Okay, so we're going to go back to the, go back here. And it may take another minute or so to finish. So here I want to briefly point out that what I'm plotting here is the multi-electron intensity. So if I go back to the single electron, then we'll see. Yeah, here we go. So this is what I wanted to show. So we've opened up the aperture, and so we see that you get the shape of the undulator radiation, and then that's passed down. And here I'm also plotting the multi-electron intensity. Let's go back to the single electron intensity, and you can see that that's nicely focused here. So there's certainly, you have to play around a bit with these different propagation parameters, but you can get some pretty good results here. Okay, that's pretty much what I wanted to show. So I'm available for questions now. Thanks very much for paying attention.
Thank you, Boaz, for giving us that presentation. Quick reminder, please use the Q&A button at the bottom of your screen to submit any questions that you might have. And we will go ahead and do just a couple minutes of Q&A here, since we were a bit long on our time today, but we had a great presentation. So we'll start with our first question in line, which is, how do we see the impact of the electron beam on the radiation in SRW?
Okay, yeah, that was what I was actually just showing here. So the electron beam is, when you plot the single electron intensity, that's what you get. That's what the radiation from a single electron. Whereas if you plot the multi-electron intensity, then you'll see that it gets spread out, because that's you get this wider electron beam with a non-zero emittance, and so that's where you get it. And this is where the partially coherent, this works in the simple case of not having an aperture. If you if you don't have if you do have apertures, then this convolution theorem doesn't hold, and you'll need to get a little deeper into the partially coherent calculations to take the electron beam into account. But in this simplest case, you can just plot the multi-electron intensity, and you can see the impact of the electron beam.
Excellent. Thank you very much. And then our next question in line is, how do I decide which propagator to use in SRW?
Yeah, so let's see. So that's basically, if you look in the propagation tab here, you can see that each one of the elements has a number of properties associated with them. And so for a drift in particular, the drift is doing a Fresnel transform, and so if you stick on with standard, that's going to be the standard transform, but this quadratic term is an interesting calculation that Oleg has done to pull out the very rapidly oscillating term in the radiation, and then that means that you don't need as high of a resolution. So I think if possible, you should use these quadratic term propagators for the drift. If you're running into trouble, you can always try the standard, but and then also if you're going from a waist or to a waist, sometimes this quadratic term can get into trouble, and you may want to try the specific propagators for the from waist or to waist. But it takes a little bit of playing around, but with some knowledge, you have a lot of freedom here to choose from these different propagators.
Excellent. Thank you very much. We are at 55 minutes, so we need to wrap up our time for today. But thank you again, Dr. Nash, for that presentation.